Everyone. So this is my topic for today's video lecture is stereochemistry of carbon compounds, and I'll be giving the basic informations about it. Let us now go into the first slide. So, so if you see this reaction, this is a very simple reaction where I have an aldehyde and it is reacting with cyanide to form the cyanohydrine, and it is a very simple reaction. So we expect just a single product in this case, but actually it is not the case because we have in the aldehyde it has two phases. Okay, so you can see the pi star orbital here in this one. So cyanide can attack either from the above the plane of the board or from the behind of the board. So it has two phases. Okay. So what happens if the cyanide is approaching from the top? Okay. So if it is approaching from the top, then it ends up the cyanide, the nitrile group ends up on the above the board, and hydroxyl group ends in the behind the plane of the board. Okay, this is the one, and the other case where cyanide is approaching from the back face of the carbonyl group, and so it attacks from the back face. So hydroxyl ends up on the top of the plane of the board, and nitrile ends up pointing back. So now what we see is product A and product B. Okay, so in the product A we have cyanide on the above the plane of the board, and in product B cyanide is behind the plane of the board. So if I see these two products, they are not the same molecule. So we have two products in the reaction of aldehyde with cyanide, and the cyanohydrine form are two different ones, product A and product B. If I do a mirror image and then rotate, and we get the product B. So they are non-superposable mirror image. Okay, so they cannot be superimposed on the mirror. So let us see from the model, it will be easier to understand. So if I consider this one, in this case we have the cyanide. So this one, let's see like this. So the blue one, the sky colored one is the cyanide. So this is coming on the top of the plane of board, as is the view direction. This is the above the plane, this is the behind the plane, and this is the CO2H1 side. And the other one where we see the other one is this. Okay, so this is virtually the mirror image. Okay, so in this case what we have is cyanide is behind the plane of the board. So we have two different products. This is product A where cyanide is above the plane of the board, and here cyanide is behind the plane of the board. So we have virtually two products, and they are actually mirror images of each other, but they cannot be superimposed. If I put a mirror over here and like this, if I put, then we get the product B. So they are non-superposable mirror images of each other. So enantiomers. So this product A and product B are called enantiomers. So enantiomers are structures that are not identical. So these are not two identical molecules again, and they are mirror images of each other, but not superposable on each other. Okay, and structures are chiral if they have non-superposable images of each other. So chiral if they cannot be superposed on their mirror image. So I call this carbon as a chiral carbon, and these two are enantiomers. Okay, product A and product B. So chiral objects, and you can see here also some examples in our daily life. We have the handedness. So this is our right hand and left hand like this. Our feet, gloves, the golf clubs. So basically the right-handed gloves and left-handed gloves are not superposable with each other. So they are kind of a, you can give an example. This is the analogy of an enantiomer. Okay, so now what are then the chiral molecules? So here we see another reaction where we have the over here and the methyl group over here, and sorry. So this is the methyl group. Two methyl groups are there, and it is the same reaction with the cyanohydrine, and we're getting acetone cyanohydrine. So here also the same thing can happen. So cyanide can attack from the top of the plane of the board, and it can also attack from the behind the plane of the board. Okay, so in this case we see the resultant two products C and D. But what happens here is that these two products C and D can be interconvertible by simple rotation. So they are not they are superposable mirror images. So that's why this molecule is an example of chiral molecules. Again, if the molecules are interconvertible by simple rotation around the axis, then they are a chiral molecule. Okay, so let us now go to the some basic things about this stereochemistry and how we can relate symmetry elements and chirality. Okay, so we see here simple axis of simple or proper axis of rotation, that is the symmetry Cn. This is a rotational symmetry. This is related related to the chirality. The plane of symmetry sigma and the center of symmetry I. These are all these are a reflective symmetry, and this one is also a reflective symmetry, which is called the alternating or improper improper axis of symmetry. And absence of Sn is the necessary and sufficient condition for chirality. That means if Sn is absent, that means the alternating or improper axis of symmetry is absent, then the molecule should be chiral. Okay, so let us now just give say a little bit about the element of symmetry. So this is the simple axis of symmetry. You see C2 over here. If you rotate this molecule, this one, the G comes over here, 180 degree you rotate, and you get the same indistinguishable structure. Okay, so what is C2 then? Then the 2 comes here is nothing but the rotation. Okay, so I have 360 by 180, and that gives me C2. Okay, so that is 2. So the subscript 2 defines as how much angle I have rotated to get the same indistinguishable structure. So 360 by 180 is 2. The other one, the center of symmetry, if I start with here, go through this point and end up here, we'll get the same point in the other side. So this is another element of symmetry and called the center of symmetry. This one, so basically I am showing a group G, which is a sec-butyl group having this structure. Again, here G, I rotate 90 degree and in the molecule, but within this axis, and what I get is here is that this comes here, and then I reflect to the plane perpendicular to it. Okay, so what happens is that then I get the indistinguishable structure. So this is the alternating axis of symmetry. So again, the 4 subscript transforms 360 by 90. Okay, so I rotated 90 degree and then reflected a plane perpendicular to it, 90 degree plane, and I get the same indistinguishable structure. And if a molecule possesses the reflective symmetry, such as the center of symmetry or this Sn S4, this is the alternating axis of symmetry, then the molecule is chiral. So that is chiral. Okay. Now, there is a very important thing, relation with the plane of symmetry. So chiral molecules have no plane of symmetry, sigma. So if I see that these two molecules, they do have plane of symmetry here that passes through this. So the plane of symmetry runs to the central carbon, the OH and Cn. Okay, and to methyl this side, this molecule also have a plane of symmetry which is orthogonal to the paper. Okay, so none of this molecule is chiral. So none of them is chiral. So these are achiral molecules because they have plane of symmetry. Now, what about these two molecules? They do not have the plane of symmetry here, because if I pass a plane like this, I don't get that one part is not the mirror image of the other part. The same thing is over here. So does not contain any plane of symmetry. So they are mirror images of each other and they are enantiomers. So chiral molecules should not have any plane of symmetry. In that case, if they do not have the plane of symmetry, they will exist as enantiomers. Okay, so now the basic 2 points I have discussed so far is that any structure that has no plane of symmetry is chiral and can exist as two mirror images and forms as enantiomers. And any structure with a plane of symmetry is not chiral and cannot exist as two enantiomers. So this is the most basic points about the chiral molecules, the chirality in that case. Okay, so now another important aspect about the stereochemistry is the term configurations and conformations. Okay, so now configurations means that the two enantiomers where the bond connections can only be, so if I see two structures, they cannot be interconverted by any means rather than disconnecting the bond. So if I have two these structures and I cannot interconvert, these are two enantiomers, I cannot interconvert this to this. Only way we can do it by disconnecting this bond and connecting it differently, like this. Okay, so those are called configurations. Okay, so bonds are broken and then means that the bonds are broken and leads to a different molecule. Those are configurations. And conformations means if you rotate the same molecule and through this bond, okay, so I rotate this bond, okay, and I get the same structure. So by rotation about the bond and a single bond without breaking them, I lead to the conformation. So again, configurations means you cannot interconvert between the two these structures. The only way you can convert is to break a bond and connect it differently. So you need to break a bond for configurations, but conformations means the same molecules is rotated around a single bond and it rotates like this and get different conformations. So this is the two important terms in stereochemistry. One is the configuration and there is a conformation. Okay, so now we go to a very interesting thing that is called the designation of chirality. Okay, so so we must designate each chiral center in such a way that when we say this is the molecule and we can draw the structure in that case. So how it is how it is designated is with the description R and S. So there are some rules, and based on the Kahn, Ingold and Prelog rules, CIP rules, and we have to assign the priority according to the atomic number, and then we decide the priority according to the CIP rules. Okay, so we see here, and this is the chiral center, and marked as a star, and we see there are 4 different groups. So so this is a chiral atom, which the chiral carbon atom, which has 4 different groups attached to it. Okay, so chiral center or stereogenic center, and now I need to designate the priority. So I see NH2 is there, CO2 is here, Ne is there, and hydrogen is there. Okay, so priority will be according to the atomic number. So nitrogen, then carbon, both cases carbon, but in this case next atom is oxygen, but in this case next atom is hydrogen. Okay, so this is higher priority. So because oxygen has a higher priority, higher atomic number than hydrogen. Then finally the last group, that is the hydrogen, is the least priority one. So now I can designate the 4 different groups according to the CIP rules and assign them their priority. So 1 amino, then CO2H, then methyl 3, and then hydrogen. Next thing is that I have to put the lowest priority group, that is the hydrogen, behind the plane. Okay, now we see in this structure it is above the plane. So I rotate and put the hydrogen behind the plane. So I see now the arrangement is like this. So hydrogen is now, I rotated the molecule. I said that if I rotate around single bond, it's the same molecule. Okay, so it is hydrogen behind the plane. Now we have amino here, NH2 is 1, this is 2 and 3. So now I mentally think the direction of rotation, and we see this is anti-clockwise. Okay, so it is rotating anti-clockwise, 1, 2, 3. Okay, so that is designated as S. And this is the name of the compound is alanine. Now for this case, we see the lowest priority group is behind the plane, so that is pointing to into the paper. And now 1, 2, 3. So the rotation is now is clockwise. So this is R. So this is R lactic acid. So we see S alanine, R lactic acid are two enantiomers. So this is the way to designate the chiral carbons. Okay, so now say a little bit about the enantiomers. So I have told that enantiomers are non-superposable mirror images of each other. Okay, so what about their chemical and physical properties? Is there any difference, or they are the same molecule, everything will be same, so we cannot say, just the way we write them, that is the difference. So is there a chemical difference between two enantiomers? And the simple answer is no, there is no chemical difference. The enantiomers have identical NMR spectra, they have identical IR spectra, they have identical physical properties such as their melting point, or if it's liquid, it's boiling point, and all these things. So these are all identical, so we cannot distinguish them. But there is a certain way we can distinguish between. There is only a single important exception, and that is rotation of the plane polarized light. Okay, so that's the only way we can differentiate between two enantiomers as R and S. R enantiomers. Okay, so let us see this. What is a plane polarized light? Just a little bit say about this. So you have a light source, light coming, and this randomly oriented unpolarized light. So what we see in your eyes outside, all light is vibrating with electric field and magnetic field vibrating in all the directions. So these are unpolarized light. Then I pass it to a polarizer, which what is its job is to make it polarized in a plane. So light is vibrating in a single direction. So now if I assign this plane polarized light to the compound, so such as the enantiomers, I see that S-alanine, if I shine the plane polarized light, the light is rotated to the right. And if I shine plane polarized light to R-alanine, the light is rotated to the left. So this is the difference now. Okay, so the two enantiomers now can be distinguished. So I see that one enantiomer S-alanine is rotating the plane polarized light to the right, and R-alanine is rotating the plane polarized to the left. Okay, so this is the important difference. And if I have a mixture, say, and there we have 50% of S-alanine and 50% of R-alanine, both present in the same amount, then that is called a racemic alanine, and that will not rotate the net rotation will be 0. So the light will pass unrotated. Okay, so this is the racemic mixture, racemic alanine. So I can distinguish between the different enantiomers, S-alanine, R-alanine, and the racemic alanine in that case. So I will continue with this stereochemistry series in the next lecture also. Hope you have a good time. Thank you.